Hey guys, Assalamualaikum. Welcome back to another virtual lecture. In today's video, we're going to do a bit of tutorial on hypothesis testing for a population mean when the population standard deviation is unknown. In the next few examples, we will see how to apply the 6 steps procedure for hypothesis testing as well as the calculation of p-value. Let's take a look at this first example. The management of wine industries is considering a new method of assembling its gold cart. The present method requires 42.3 minutes on average to assemble a cart. The mean assembly time for a random sample of 24 carts using the new method was 40.6 minutes, and the standard deviation of the sample was 2.7 minutes. Using the 10% level of significance, can we conclude that the assembly time using the new method is faster? Also, find the p-value. Okay, before we begin, try to identify all of the information given from this question. So from this question, we can see that the mu, or the population mean, is 42.3 minutes. Okay, so you can write it down, right? Or if you're a fan of highlighting, feel free to do so, not a problem. And we also know that the x bar, or sample mean, is 40.6 minutes, okay? So I think this is one of the most important steps because many students tend to get confused which is which. Okay, so please identify first which is mu, which is x bar. Okay, also from this question, we know that the sample standard deviation is 2.7 minutes. So we can put that here, 2.7. And finally, the sample size given is 24. Now, step 1 is to basically write down the hypothesis, right? So we know that the null hypothesis is at the top and the alternate in the bottom. So now let's take a look at the question. They're asking us, can we conclude that the assembly time using the new method is faster? So that means this particular clue is actually for your alternate hypothesis here. Okay, so how would you write that? Remember, the way to write the hypothesis is always for the population. Therefore, it must always be mu here. Okay, remember this test here is a hypothesis testing for population mean. So obviously, that is what the hypothesis is about. All right, so anyway, back to this clue from the question. Can we conclude that the assembly time using the new method is faster? So meaning we are hypothesizing that since it's faster, it should be less than 42.3 minutes. Okay, so this would be the alternate hypothesis because, as I mentioned to you before, the sign for the alternate will always be inequality sign. That means it's either less than, more than, or not equals to. Okay, so what's the opposite of this? The opposite of less than sign should be here for the null hypothesis. So you actually have a choice. You can put here as greater than equals to, or you can also put it as equals to. Not a problem. Okay, again, I repeat, you can put the sign here as equals to or greater than equals to. Okay, which is the opposite of less than. Okay, so this would be our first step, writing down the hypothesis. Now, step 2 is basically to determine our alpha, which is given in the question. Alpha is 10%, guys, so we can just put it here as 0.1. Okay, it's 10%. And let's see here, is this a one-tail or a two-tail test? Remember, a two-tail test, the sign of the alternate does not specify any direction. Whereas a one-tailed test, the sign for the alternate hypothesis specifies a particular direction. As you can see here, this points less than, so it is showing a particular direction. Therefore, this is a one-tailed test. All right? Okay, some students ask me, do I have to write it down here? Actually, no. This is basically just for you. It's for your own guidance and reference. Okay, now step 3. Okay, step 3 is the only step that we actually calculate something. Okay, the rest of it is just referring to the tables. Okay, let me just drag it down here a bit. So step 3 is basically to calculate our test statistic, right? Calculate our test statistic. Now you need to determine first what kind of test statistic do we want to adopt for this question. Let's go back. Okay, so as I mentioned to you before, we have an option. We can either use the Z distribution or the T distribution. Now in this question, let's see back all of the information that we know here. Should we use the Z or the T? Okay, from the information given here, we should use the T distribution for 2 reasons. Number 1, we do not know the population standard deviation. We only know the sample standard deviation. So that should be the biggest clue. Secondly, we have a small sample size. So these two are the main reason why we should be using the T distribution, okay? Let me just drag it down again here. So we're going to use the t. Okay, so please, of course, justify. You can put it here. Use the t distribution because, okay, because why was it just now? We have a small sample size and sigma is unknown. Okay, so justify, right? So we want to calculate the test statistic using the t distribution. Okay, remember the formula, x bar minus mu over the standard error. Standard error is s over the square root of n. Okay, so basically now what we're going to do is just going to plug in all of the numbers that we've identified earlier. Okay, so x bar was 40.6 minus mu, which is 42.3 over, what was this? Sample standard deviation is 2.7 over the square root of n, which is 24. Okay, maybe you want to pause the video for a while and try to work that out. Okay, so I'm going to give you the answer here, which is minus 3.084. Okay. Okay, I realized I didn't have much space, so I'm just going to create a border here. Now, step number 4. Okay, remember, in step number 4, we need to do two things. One is we need to determine what our critical value is, as well as the rejection and acceptance area, and then we need to write down the rejection rule. Okay, so here is basically our distribution. Now remember, we're going to use t now, not z. Okay, but the center here is still 0. Okay, so we know that this is a one-tailed test. Okay, so now to sketch or to determine which one or where is the rejection area, we need to go back. Okay, go back to the first step. Okay, now take a look at the alternate hypothesis. Okay, we are hypothesizing that the population mean is less than 42.3. Now we know that when we standardized 42.3, we get 0. So anything less than 42.3 means anything less than 0. Okay, so let's go back here. Less than 0 means the rejection area is to the left. Okay, so here would be our rejection area. So we write it down, reject the null, and here is basically our alpha, which is 0.1. Remember, since it's a one-tailed test, the entire alpha goes to this shaded region, okay? And here would be our acceptance area. So, meaning we would not reject the null if our test statistic falls in these areas, okay? Now we know that the value of t that separates the acceptance area and the rejection area is called the critical value. So here's our critical value, TCV. Now in the previous videos, we've looked at how to find the critical value when the distribution was set. This time around, the distribution is t, so it's going to be a little bit different. Okay guys, so this is our t distribution. Okay, so now when we want to find the critical value using this table, we need two things, okay? The first is we need to know what our degrees of freedom is. Here, degrees of freedom is simply the sample size minus 1, okay? And then we need to focus on this part here. Okay, remember when we studied confidence interval, we were only looking at these two rows, right? Confidence interval and the confidence levels. Okay, now we ignore these two rows. Now focus on the remaining 4 rows. Here we have to focus on the level of significance, and we need to know whether the test is a one-tailed test or a two-tailed test. Okay? Now back to our example. We know that our test is a one-tailed test, and the alpha is 10%. So basically we need to look at this column. Now let's drag down and find what our degrees of freedom is. Our sample size is 24, so 24 minus 1 would be 23. So again, I repeat, look at this column. Okay, one-tailed test, 10% alpha, and degrees of freedom, 23. So basically, this is our critical value, 1.39. Right, so from the table just now, we've identified that the critical value is 1.319. So now since it's to the left of 0, it is actually minus 1.319. So now we can start writing our rejection rule. So we need to reject the test statistic if it falls in the rejection area, which is less than minus 1.319. So let's write it down. Reject the null if the t, meaning the test statistic, is less than minus 1.319. 9. So this is our rejection rule. And of course, for bonus point, we can write down the working for our degrees of freedom just now, which was n minus 1. So our n was 24 minus 1, so it's 23. Now we move on to step 5. In step 5, we need to compare the test statistic that we've calculated in step 3 against our rejection rule. Okay, so we just compare. Okay, so where does our test statistic fall? Does it fall in the acceptance area or does it fall in the rejection area? Now, minus 3.084 is very small. Okay, so it's definitely to the left of minus 1.219. Okay, so we can just mark it here. Okay, so here it is. Okay, so we can see that the test statistic falls in the rejection area. Okay, so we can make our decision, which is to reject the null. Okay, so we can write it down here. Since the test statistic falls or lies in the rejection area, okay, we reject the null. Okay, you can highlight or underline this for extra emphasis. Okay, now this is our decision, and don't forget step 6. Okay, you can actually combine step 5 and 6 together. Step 6 is basically to interpret or to make a conclusion based on the context of this question. So to do step 6, let's just go back to our first step. Okay, so first step is actually very important. Okay, so we've decided to reject, right? So we've rejected. Okay, meaning if we reject the null, means we will be taking the alternate. So how can we interpret this? This is basically what we got from the question. So we can say that we have enough evidence to suggest that the assembly time using the new method is faster. Okay, it's very simple. So we can write it down here and can conclude that the assembly time using the new method is faster. Sorry guys, not enough space, but you get the gist, okay? Now the question also asks us to find the p-value. Now the way to find p-value using the t distribution is very different from the z distribution, okay? So how to find the p-value when our test statistic is t? Let's look at the t table. Alright guys, now to find the p-value when our distribution is a t distribution, okay, what we need to do is we need to first of all determine where is the location of our test statistic, okay, along the lines of our degrees of freedom. So just now we know that our degrees of freedom is 23, right? So along this row, try to locate where does our test statistic fall. Our test statistic just now was minus 3.084. So we can ignore the negative sign for now. So 3.084, where does it lie? Somewhere between here, right? So 3.084 is in between 2.807 and 3.768. But this is not our answer yet, okay? So to find the answer, we need to drag up and see where it compares against our alpha. Okay, let's go back up. We know that our test is a one-tailed test. So just now we were here, we go up, one-tailed test. So this is our answer. So basically, our p-value is between 0.005 and 0.0005, very, very small. Okay, I repeat, our p-value is between 0.005 and 0.0005. So how to interpret? Since the p-value is very, very small, much smaller than our alpha of 10%, we have evidence to suggest that the null is false. Therefore, we reject the null hypothesis. Okay, so now let's take a look at our next example. Employees in a large company are entitled to 15-minute coffee breaks. A random sample of the duration of coffee breaks for 10 employees was taken at the times shown below. Okay, so these are the times. Assuming that the times are normally distributed, is there enough evidence at the 5% significance level to indicate that, on average, employees are taking longer coffee breaks than they are entitled to? Also, what is the p-value? So as usual, try to identify all of the information given to us. Okay, so here we know that the sample size is 10. Okay, so we can put it somewhere, n is 10. And we were given this first line, yeah? Employees in a large company are entitled to a 15-minute coffee break. So this would be our mu. Okay, it's the hypothesis. So this is our mu. Now, we are not given, however, the sample mean, right? But we are given several information. Because it says here a sample, a random sample of 10 employees was taken with the times shown. So this 12, 16, 14, 18, etc., and 60 minutes. These are all of the individual raw data, individual coffee breaks taken by these 10 employees. So why do you think they give you this information? It is so that we can calculate the X bar. Okay, so X bar is not given as a figure, but it's given information, so that's what we need to do. And besides X bar not being given, the sample standard deviation is also not given. Okay, so this is basically the difference between this example and the previous example just now. You have a choice. You can either show all of the workings to find X bar and S first, then only proceed to doing the 6 steps hypothesis testing, or you can show this working somewhere in step 3. Okay, personally, I prefer to show the workings of these two first, then only go and do the 6 steps hypothesis testing. Okay, so now let's find our X bar and S first. Okay, X bar, or sample means basically the sum of all of the values of X over the sample size. So we know the information here, 12, 16, 14, 18, 21, etc., etc. So we just put it here. Okay, so 12 plus 16 plus 14 plus, okay, you write in full, okay, so I just want to make this quick. So over 10. Okay, so we basically here we have 166 over 10. So basically our X bar is 16.6. Okay, now the next thing we need to find is the sample standard deviation. Personally, I don't mind if you would prefer to just calculate it using the formula, or alternatively, here's a more organized method to showing your workings. You can just, list down all of the values of X that's given to you, and then you show the working via, like a table style manner. Okay, so just now we already know that X bar is 16.6, right? So what we need to do is take all of these individual X values and just minus the sample mean, square it. Hence here we will find the squares. Okay, and then we add it all up. So this is basically our sum of squares. Once we have our sum of squares here, we can just input everything in the sample standard deviation formula, which is this one. Okay, and we'll get the answer, 2.59. Now that we know the sample mean and the sample standard deviation, okay, we can go on with the 6 steps hypothesis testing. Okay, so step 1, as always, we want to write down the hypothesis. So if you look back at the question, we know that the population mean is 15, sample mean is 16.6, sample standard deviation is 2.59, and the sample size is 10. Okay, so these are the information that we know. Now to write down the hypothesis, which is step 1, let's look at the question. It's asking us, is there enough evidence to indicate that on average, employees are taking longer coffee breaks than they're entitled to? So average here, what are we testing? We're testing the mu, okay? So always write mu in step 1. Okay, longer than. So the key word here is longer. Longer shows what? Greater than, right? So we know that anything that shows a particular direction, that belongs to the alternate hypothesis. So let's write our hypothesis. Okay, the null is always at the top, followed by the alternate. So they give us that employees are taking longer breaks than they're entitled to. Mu greater than. What are they entitled to? What is the mu? Mu is given as 15. Okay, so this is our alternate hypothesis. Our null hypothesis, okay, here you have a choice. You can either put it as equals to 15, or if you want to put it as less than equals to 15 is also acceptable. Okay, now step 2 is to basically write down what our alpha is, and our alpha is given as 5%, right? Yeah, so 0.05. Is this a one-tilt or a two-tilt test? It's a one-tilt test because the sign of our alternate hypothesis shows a particular direction. Okay, previously it was to the left, now it's to the right. Right, now step 3 is to calculate our test statistic. Okay, now just like before, we've got a small sample size and we do not know the population standard deviation. So again, we will use the t distribution. Okay, so please justify it somewhere. T is basically x bar minus mu over the sample standard deviation over the square root of n. So we will just plug in all of the numbers that we've identified earlier. 16.6 minus 15 over 2.59 over the square root of 10. So why don't you try to work that out? Okay, so the answer would be, okay, you'll get here 1.6 over 0.82, and we'll get 1.95. Okay, so 1.95 is our test statistic. And then next step, step 4, okay, we need to do two things. Okay, we need to basically write down our rejection rule. But in doing that, we can also show our critical value and the rejection area. Okay, so here, again, is our t distribution. When we standardize the mean, we'll get 0. Again, we can see here it's a one-tailed test. So where's the rejection area, to the right or to the left? We can see here greater than 15. 15, when you standardize, it becomes 0. So greater than 15 means greater than 0. Therefore, this is our rejection area. Okay, so here's where we reject the null, and here all of this is our alpha. Okay, 0.05, because it's a one-tailed test, therefore all the alpha is put in one place. Here's our acceptance area where we do not reject the null hypothesis. Okay, now we want to show what is the critical value here. Okay, just like before, you go and look at the t table. Why don't you do that on your own? Okay, so what we need to do is we need to show first the degrees of freedom. Degrees of freedom here is basically sample size minus 1. Our sample size in this question is 10 minus 1, so degrees of freedom is 9. Okay, why don't you look at your t table? Look at degrees of freedom 9 and look at one-tailed 5% alpha. Okay, so you will find that the t is 1.833. Okay, so I'm going to write here straight away, 1.833. All right. Now, next step, step 5, what we need to do is we basically just compare the test statistic that you calculate in step 3 and see where does it lie. Does 1.95 lies in the rejection area or in the acceptance area? So we know that 1.95 is more than here. Oh, guys, I'm sorry, I forgot to write down the rejection rule. Okay, let's write it down first. Okay, do not forget to write it down. So we need to say reject the null if the test statistic is here, greater than 1.833. Okay. Anyways, just showing you that in case you forgot, you can always just write it down there. Okay. So here we can say that 1.95 lies somewhere here, right? So you can just mark it. And we say since the test statistic lies in the rejection area, we reject the null hypothesis. Okay, this is step 5. And don't forget, we also want to do the interpretation or conclusion, which is step 6. And we can conclude that, okay, to conclude, we just go back to step 1. We're saying we want to reject, right? Rejecting the null means we are taking the alternate. So what does this mean? In a way, we're agreeing with the hypothesis or the alternate hypothesis. We're saying that the employees are, in fact, taking longer coffee breaks. So we can say that we have evidence, conclude that there is sufficient evidence to suggest that on average people take longer coffee breaks. Okay. All right? Okay. So why don't you try and find the p-value in this case? Right? So remember, to find the p-value using the t distribution table, we need two things. One is the degrees of freedom, and secondly, is it a one-tail or a two-tail test? Okay, so our degrees of freedom for this question is 9 because our sample size is 10. Okay, so 9. And then what do we need to do? We need to find along this row of our degrees of freedom, we need to identify or locate where is the position of our test statistic. Now, our test statistic just now was 1.95. So look here, this is 9. 1.95 is somewhere here. is between 1.833 and 2.262. So it's somewhere here. So the answer would be, the p-value is, you bring it up here. So we know it's a one-tailed test. So our answer, p-value, is between 5% and 2.5%. Since the p-value, 5% to 2.5%, is much smaller than alpha, which is 5%, we can say that we have evidence to suggest that the null is false. Therefore, we reject the null. Here, just in case if you're wondering, this is one way to write the p-value, okay, for this question.